Alright, today we're taking a look at Green's theorem after we discussed curl, because curl is necessary to understand Green's theorem. So the first thing I wanted to point out is that we've calculated circulation in a myriad of ways, as well as flux. But Green's theorem applies to circulation, and so that we decided was equal to, it's a vector line integral of the vector field dotted with the unit tangent vector of the path, r of t, times the small segment length for each chunk of the path, ds. Well, we also learned how to write that in its more general form, which was f dot dr. Because dr is the same as the magnitude of dr is ds, and the tangent vector holds the vector information of dr. So, if we want to rewrite circulation, we could say, well, let's write f in terms of its x and y components. So we could write the vector field with an x component of m and a y component of n, or q and p in some textbooks. But because I used m and n for the time derivation of flux, I decided to go ahead and stick with m and n. And so if x has m and n x and y components, if f has m and n x and y components, then we could go ahead and say that dr has dx and dy components. And knowing that, we look at the dot product of f dot dr. Well, if we dot mn dotted with dx dy, then m times dx is m dx plus n times dy, which is n dy. And just like that, we have a new form of circulation. This is like the circulation form of the time flux derivation that I did a few videos ago. So what's interesting now is we're going to find a way to relate curl to this. So let's say that we take a path, a closed path, and it's going to go in a counterclockwise direction because convention states that flux is positive when there's a counterclockwise rotation from your perspective. But that's all it is, it's just convention. But it's important to know. So the idea here is that if this is our path that's dictated by the vector curve r of t, what we can do, and of course there's a vector field lying within this path. One thing that we can do is we can cut this path into a quadrant, for example, and we could actually do counterclockwise motion in each quadrant. We'll do a counterclockwise one here, and then for this one we'll also go counterclockwise, 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 and what you'll notice is that the external counterclockwise on the boundaries remains the same, whereas on the inside of these quadrants, you'll notice that the paths go in opposite directions. Now, if you take a vector line integral one direction, you will get a value. If you take that vector line integral the opposite direction, you will get the negative value of that value, or the opposite sign, whatever it happens to be. These will cancel. And so what we decide to do is cut up this external curve. We're going to cut it up into many, many small pieces. And we're going to call those pieces dA. The reason why we're going with dA is because Green's theorem is for 2 dimensions. We'll be covering Stokes' theorem later on, but the concept's very similar. So the idea that these cancel, those line integrals cancel, tells us that also, so if we were to take, say for example, the flux, or I'm sorry, if we were to take the curl of the vector field of dA, so in other words, the curl of the vector field, so nabla cross f dA, that's going to be a double integral, that you'll notice that if we look at every little dA and we do a counterclockwise, let's see, that was counterclockwise, a counterclockwise curl for every dA, these points cancel out, leaving us with only the boundary of the curve. And so just like that, we've proven in a conceptual way that if we take the curl and integrate it for all little chunks of area, that we are actually going to end up with this closed loop, and that would be the integral f dot dr, which is also circulation. And so what we've just now proven is that we could write a single integral as a double integral. And the reason why we do this is because sometimes it's easier to, like for example, sometimes it's easier to calculate circulation using this method. Sometimes it's easier using this method. And rarely it's easier using this method. But we're just finding another method because sometimes it's very difficult analytically to solve for any of those. And so now that we can relate it to a double integral, let's go ahead and solve. Alright, so we're using m and n for the f components, and for the dr components we are using dx and dy. So we're in 2 dimensions. Now we know that nabla is going to be, so if we take the cross product of nabla and our vector field, that's going to make us set up this determinant. And nabla, of course, is d dx, d dy, and d dz. But I would just like to point out that because we are living in a 2-dimensional world, in other words, our whole graph lies in 2 dimensions, that the rate of change of anything with respect to z is always going to be 0. So instead of writing d dz there, because we're only in the xy plane, I will replace that with a 0. And then of course our f, we could write in components of n for the x direction and n for the y direction, and then a 0 over here. So if we go ahead and take our cross product, I is 0, 0, so we get 0, 0 for I, j is 0, 0, and k is dn dx, dn dx minus dm dy. And because these are all zeros, what we can figure out there is that actually that nabla cross f is in fact equal to dn dx minus dm dy. And so we can also write this equation right here. Let me get rid of some space up here. We can also write this, so we could say that, okay, circulation is equal to the closed line vector integral of f dot dr, which we proved conceptually equals to the double integral of nabla cross f dA. And now we further simplified it using this into a double integral of dn dx minus dm dy, and dA, which of course we can write dA as dx dy. So this is the conceptual method of Green's theorem, which relates the curl with the external curve, the enclosed curve. So anyways, this is kind of fun, it's interesting, and it's going to be useful for certain problems, so I hope this was helpful, and I'll see you next video.